to studies, back to week 7 now. I wish you had a good break with getting some studies done. And this week we will go through another process to make sure steel beam or a steel beam is designed in the right manner, if you like. So what we've been going through so far, we've had a steel beam, and we know how to find or check its. Let me just use a different slide, but I don't have it open for now. So yeah, that's when this is open. So we've gone through the process of finding the bending capacity. Yeah, the bending capacity. So that was all about finding phi MB, and we critically going through the two main capacities that we may have there, depends on if it's fully restrained or not. So the first one was to do with MB, that was MS, the section capacity, and MB was the bending capacity. So that was all to do with finding the bending capacity of the section. And at this stage, if you manage to find it successfully done, what does it mean? If your capacity was actually more than or equal to the action, then that means your beam is strong. Is that the end of the story? No, you still need to make sure it's going to be strong in shear, right? Typically here. And you should also check it to be strong in all other actions that member may experience. So you know from mechanics of solids that some members may have tension, axial load in addition to shear and bending. So in that case, you have to also do a tension check or a compression check. You can't have tension and compression together, and it depends on, I would just call it axial load. Yeah, so today we're going to go through this shear check, and in the coming weeks we're going to go through axial checks, and regardless whether it's going to be tension or compression. So what we're doing here overall, we're actually doing strength check, which is making sure the beam will not break from whatever actions it is under. And still, it's not enough. We have to check it for serviceability. Serviceability means the beam is not sagging a lot. There's a lot of beams which will not break. That means which are strong. However, they are sagging a lot beyond the limit requirements or beyond the actual service requirements. For example, if a steel beam is carrying a very special glass feature, the glass will break if its support have actually sagged a lot. So that means we have another check, we call it, so that was all strength here. And we have another check which is to do with serviceability, and a serviceability check is the other thing we're gonna do today. So we're gonna go through simply today or this week, we're just gonna cover shear and also serviceability. In the coming weeks, we're gonna take you through axial loads. There's a lot of members can be under compression, like columns. They typically under compression load, and we're going to take you through that process. There's a lot of other members which takes tension, and that will also be covered in a separate in a week. In, I would say, week 9 or 10. One of the weeks we're going to go through. The good news, guys, is really the subject's gonna be kind of not that lengthy in terms of the information you need to understand and learn, but I want you to fully understand the conceptual design and how you build an engineering concept to know really how to use this skill in the real world applications, and that's where we're gonna try to get you to. It's not only about this equation is used. Today is really straightforward topic. It's all about using overall 3 equations, 2 of them going to be for the shear design, and only one relationship can be used to check whether a beam is actually sagging a lot. That's the whole idea of today. So it's really a straightforward topic today. And next week is going to be other actions. So we'll take it step by step. So this was just again where we are at. Week 7 is going to be again about shear and serviceability. Right now, someone will ask, are these the two things where we check things? So bending, shear, compression, tension, they are all to do with strength. So the red ones are to do with strength, to make sure it's strong, and depends on if the member is suffering from such action. Serviceability, it's another criteria. All right, is that all what we do? Most 80% of what designers design for, yes, they design for these two things. I'm talking about timber and steel. Now, what about fire check? What about other kind of durability checks? They are not very applicable for steel and timber. Why? Because fire checks, usually we leave it to the architect. The architect typically going to document how he need to cover the steel structures, because you can't do much with the steel. Steel is a steel, and the only advices we give there is spray some cementitious material on a big structures. Like sometimes you see some steel members are sprayed with this ugly looking cementitious product, or we don't do this in residential projects. They're gonna just cover it with fire rated plaster. So it's nothing really to do with the designers when we talk about fire rating, unlike concrete. So there is other checks. There is crack control checks. Well, here this is to do with concrete. What I'm trying to say, there are other things, but not 80 to 90% of what the designers do on their day-to-day activities is really to design for the strength we're covering here for you. And serviceability is very, very essential. You can't just design for strength and don't worry about serviceability, because your beam will not work. This is, again, we're still working with this standard, which is almost the one before the last. We still have one standard to let you use, which is the timber standards. We're going to start talking about timber in week 10. So we're still working with the steel standard, and this is the chapter if you want to use this book as your reference. So as I said, the structure is really straightforward. We're going to just take you through the two famous equations the standard gave us to use and check the capacity for shear. It's not as puzzly as we've seen with bending capacity, where we have to decide whether we're going through MS or MB, and we're going to go through other formulas and relationships within this guy, right? Same thing for MS. I think the challenging point with MS was about ZE. Now, as I said to you 2 weeks ago, ZE can be just directly picked from the table if the question was not asking you to find how it was calculated, or you need to go through basic relationships. So this was a bit lengthy process. The good news with shear is we won't have this. It's just two relationships, and you're going to see where and how they are used. Then after the shear capacity, we're going to be done with it. Then we're going to get into serviceability. And serviceability is something you're going to see straightforward. I will just introduce you to, again, some basic formulas. Part of what we're going to be talking about when we get to serviceability is we studied it in mechanics of solid. If you studied mechanics of solids at La Trobe, here we taught you about some basic simple bending formulas. And when we talked about those simple bending formulas, we introduced you to the curvature. And if you know what I'm talking about there, or if you remember it, you're almost done. So the good news is you don't need to go through mechanics of solids again. You're just going to use ready-to-use formula, yeah, like from the shelf. Ready-to-use formula. You just need to pick the correct formula and use it, and go find the parameters within that formula. And again, you need to know what you're doing while you do that, because the engineering thinking, it's going to be there. The way you use it and depends on your case. And then after you determine the sagging that your beam will suffer from, you need to correctly compare it with the standard. And that will be limitation, which we're going to show you how to do. So it's really straightforward exercise. Then we're done. We're done with the 2 design skills we want to talk about this week. Then I will just highlight to you some kind of points or like a trends where engineers can produce economical solutions in their documentation, and some other useful information. Then you can start your walked example. So shear design, usually, to put it in an easy way, when we design, this is an I section. Let's talk about an I section, and same thing applies for a PFC. When we check shear, I will take you through. I just don't want to overcomplicate. I may have a bit of time, but I don't want to overuse it. So if you remember that, I think if someone tries to plot the shear stress now, or let me explain this in a different way. If you remember when we talked about shear in mechanics of solids, that was only 2 years ago. So if this was your beam, that was just the top flange, this is the lower flange, let's say here is the support. Okay, and we have a section here, and again the section looks like that one I'm showing you up there. If you remember, we said shear can come into 2 main components. One, the famous one, is coming this way, right? The shear force is actually acting this way, and also there is a shear force which is getting into the beam, and we talked about this VH, and that was VT, and we said to you the critical shear usually is VT, and we showed you how to find such shear stresses. Now, what I'm trying to let you know from this is which component within a section like this is sensitive to shear. Is it the flange, or the 2 flanges, or the web? Right? I'm just trying to show you the background of why or how we can decide on which component within a cross section is actually critical for shear. Is it the top and bottom flanges or the web? Now, if you, I think you didn't do that, or maybe you did it in a different subject. If someone decides to plot the horizontal stresses on the section, which we talked about in mechanics of solid, the stress diagram will look something like this. This is something which comes from the basics. So this is what we call it, the horizontal shear stress diagram on the cross section. So into this page. Okay. Now from this, what we can understand that most of the stresses are actually stressing what? The web. This is the web part here. This is the web depth. And you can see 95% or 90 and above % of the stresses are actually coming to the web. This is the web, and these up and top bottom part are the flanges. All right, so flanges are here, and the web is this guy. So what does that mean? Is Mr. Webb, he's the guy who's gonna actually always suffer from shear. What does this mean? And that's what the standards concluded with saying, when you check shear, just worry about the web. That's it. So this is really the message we're trying to let you get from this slide, is simply the web is typically the element within a cross section. So basically, when you're going to design things, you're going to have I section or a PFC channel, or even other box sections. If I just put for you a PFC, which is parallel flange channel, it's like a like this channel. And again, the web is the guy who's suffering from shear. If we even have a box cross section like this, and the load is applied this way, this is again the web, usually the vertical component within the section. So the key message I want you to understand is the web element within an I section, PFC, or any other elements you would use. Most likely what you're going to use in the subject is an I section or a PFC. The web is the component who takes most of the shear action, and that's why the thing is simplified, and we're always going to be checking how the web is coping with whatever shear force. So this is the first message I want you really to get from here. And I think the other points we see on this slide, simply just talking about, you know, very well from SD1 and mechanics of solids, the action, when we talk about V star here, the action, right? It's always higher at the support. Yeah, making sense. It's so you usually higher at the support, or if we have a case where I've got a steel beam like this and then a column, 100 or 1000 kilonewton supported in the middle, also this point will be a bit shearing a lot. So it's also critical at this point because the shear force diagram will look something like this. So obviously it's going to be same here or there anyway, right? But remember here you're going to change it from negative to positive. So it doesn't matter really, because on this side you're going to be shearing the web up down, and in this side you're going to be shearing the web down up, so it doesn't matter really. Right, so that was the second statement here, and the story is you simply that what we're going to show you through with very simple straightforward equations. The shear capacity, it's called phi VV, must be equal or more than the V star, and the V star, you know how to get it from SD1 or mechanics of solids, and that's what we're going to teach you today. As I just showed you, it's highly dependent on the web element within our sections, and I think it's here for you. I think I forgot it was shown here, but it's there already. So basically, you see this whole stress area is actually coming onto Mr. Webb, so he's going to suffer from shear, and this is kind of the theoretical proof telling us that the element that will highly suffer from shear is the web, and that's why we're going to focus on it and not worry about flanges. Someone going to tell me, so why we have flanges? I think you should be able to answer me, because you remember the flanges are the guys who are going to look after bending. Yeah, so you remember when we designed for bending and we said there is a couple, and that's tension here and compression there if it's a positive. So in other words, the flange, they are the guys who are going to work for bending. And the web is the guy who's going to work for shear. That's another way of looking at it as well. Okay, and I think it's covered. This is just summarize what I was saying to you and the sketches that I was showing you. It's well documented in the standard how we can calculate this guy and find how much phi VV can take. It's clearly documented here. So we need to do two checks. Why two checks? Because we need to, as we did for bending, you remember the 5-6 cases I talked to you about 2 weeks ago when we started about bending. I said to you we need to think about the way a beam will fail, the modes of the modes of failure the beam will suffer from, whether local buckling or overall twisting or buckling in the web or buckling in the flange. Same thing for shear. We need to think about what that web can suffer from. And basically, there are two failures he can suffer from. One is a failure due to yielding. Yeah, so that means if this is again my an elevation view for a steel beam, and I'm just giving you a section where the shear is the highest, then this web may suffer from yielding. What does it mean? The yield stresses within the steel has actually exceeded the 300 MPa, which is the usual Fy value we use. So if you remember, Fy we're adopting from one steel book is 300 MPa. And if one of the failure modes that a web will actually go by is if it goes beyond FY value, and then it will start getting to plastic and the other method, but the standards don't want us to go there. So one of the failure modes is failure by yielding. And if this, to check for that or to find the member's capacity, to be within such criteria, you have to make sure this ratio is below 82, as easy as this. And you're going to see how we apply this in a very simple example. So to make sure that the beam will be within the yielding capacity limit, it's not actually going beyond 300 MPa, then make sure this argumental relationship gonna be gonna work. That, in other words, the depth of the web, so dp is the depth of the web, and tw is simply the thickness of the web. So if this is my I section, let me take Mr. V pull down. So if this is the cross section, this is what? This is dp, and this is tw. Okay, so we're always worrying about Mr. Web. All right, so if you want to find the capacity due to yielding failure, you just apply this relationship. Now, the second possibility, or the other possibility for the web to fail by, is when the web actually buckles. So if I put it in red here, maybe the web is too tall or too high, and then it will end up buckling before it's actually getting to yield. Now it depends on again how deep is the beam, how high is the beam. Usually, if it's a beam like I'm not sure if my document is available here. Hopefully it will. If I talk about a UC section, I think most of you have worked with this. This is our universal columns. Usually universal columns, as I said, they are bulky. They are almost square kind of. The height is almost same as the width. They're expensive. They're very heavy. If you look at the weights here, they're super heavy. So we use them with careful, with careful thinking about an economical design. You can't just always jump to them because they're very heavy. Compare this guy here, which is 250. It is 90 kilograms per meter. If you compare it with a UB, same height. I just need to go back. So this is a UB, almost same height, 250. See, it's 36, half of the way, even this, about, about half or 40%. So so what I was trying to say here, this guy is the UC. They are usually short, and from experience, you can always say it will not suffer from buckling, because it's really short. This height is not that high. It will not buckle if we're talking about shear design. Unlike this guy here, which is a UB, they are a bit cylinder. They are more cylinder, and their webs can go a bit too deep. So that's where it's, yes, the failure here may be due to buckling. So for you as a designer for shear, what you really, or the approach to do it, simply you can, oops, I just opened the wrong one. The approach here is simply to, what people can do, they can find these two values and understand which one gonna be the case they have. Or one of the other approaches from the start, you just go and find this relationship. You just need to go and find the value of this relationship, which is one relationship, and just make sure if it's less than 82, then go find your VV by this relationship. So simply multiply 60 by FY by the area of the web. All right, so here I'm just kind of summarizing everything to you. Step number one, you just need to go and find this relationship. This is given to you in the standards anyway. You don't need to memorize it. You need to find this ratio. Then if you find it less than 82, that means your section is bulky. It will not fail. The web, I'm talking about the web. The sections web is not cylinder, and it will not fail by buckling. It will fail by yield, and that means its capacity to resist shear can be calculated by multiplying 0.6, which means 60% of the force it can take within the web, right? This is a standard value, and again, this area is the area of the web we know about. What about if this did not work? If that ratio was more than 82, then it means that it's gonna fail by buckling. Your web, gonna buckle. And that means you need to find the VV by this standardized relationship. It's coming from the standard as well. So basically, that's really all to do with the shear capacity. Right now, I think I told you this case before. If, for example, in a real application, if your steel beam was working well with bending and was working with serviceability, deflection, and all other criteria we needed to resist, and it's because of having excessive point load on top of it, we find it's failing in shear. The solution here is not to go and make your beam bigger, yeah, because it's just going to be too costly. It's waste of money there. You can just simply put some stiffeners here, because they will help you to restrain the web and not getting it to buckle. So then you're going to rely on the yield capacity, which you can see from here. The yield capacity will give you much more than the buckling capacity. Okay, so this is just an approaches where usually if the beam is suffer from buckling in web due to shear, you can put some stiffeners, and these simply can be, if I give you an elevation for the beam, top flange, bottom flange. Let me just make the top flange a bit thinner, so it's like this, and you stiffener if there's a decent column sitting here with some bolts, and that column maybe is carrying another floor. You can simply just document your stiffener like this, maybe 12 thick. You can do the numbers for it, and that's it. So this stiffener is just here, and it can solve the problem. All right, so that was to do with the shear capacity, which, as you can see, and as I briefed you at the start, it's kind of a relaxing topic. It does not have a lot of arguments and situations where you need to check a lot from. And usually a shear question will come combined with a bending question to you. Right? So we're done with the two main strength checks we have for beams. All right, shear and beam, we did it in 2 weeks before. Now serviceability. Serviceability, as I've already said, we just need to check the sagging, and that will get what we're going to be doing. Remember, I talk about sagging because we're teaching you about beams. If we're going to talk about portal frames, or you're going to be designing some portal frame members, we design them a lot in industrial or residential structures. I will not worry here about sagging only. I will also worry about swaying. I will worry about, well, this is the sagging issue, but also when you have wind load, as you already did for your test, I will be worrying about the sag, the horizontal deflection or the swaying of the rafter, and we need to make sure it's within acceptable limits. Otherwise, all the plaster are gonna get cracked, the glass gonna get damaged. So they have to be within acceptable limits. Who says the limits? Mr. Standards, which will show you where to find them from. And sometimes, and the standards said that clearly, they say, don't just rely on me, make sure you use your engineering thinking and get it right, because sometimes you're gonna have more sensitive products. So that means you also need to, sometimes for critical cases, you need to check with the architect that this beam or that wall gonna sag by 20 mil. Are you happy or not? If he said, I'm happy with it, then leave it as it is. If not, go make it bigger. So I think these statements here are just summarizing what I've already talked to you about. Yeah, the serviceability is very critical. Sometimes, as you're going to see in the authentic or real project we're trying to let you practice, you see, I think now if you are working with us on time, you're going to see that we stopped at the bending. and from now you're going to do shear. When you're going to go to deflection, you're going to see that whatever we designed was not enough, and we have to significantly beef up that FB11 beam. It's just a very clear case study, shows you that the deflection was simply just governed by serviceability. Or sorry, what I'm trying to say, the beam size was governed by serviceability check. And someone may come and then could I have been just designing it for deflection from the start? Yeah, but if you're lucky, it did work this way this time. So you have to go through bending, shear, and all other actions you have, and then check serviceability. But you can see with that real beam we did together, I think up to now you didn't finish the story. When you're going to get to serviceability check this week, you're going to see that the beam have jumped from a UB section to a UC section, a very much heavier beam. And why that's all happening? Because we don't need that balcony to sag by 200 millimeters or 20 or even 50 millimeters. It's not acceptable, because all the plaster below that going to get cracked. And in the balcony as well, they use glass. The balustrades, they're all glass, and the glazing companies, they're gonna limit the deflection. You cannot have 20 mil sag here. This is the column. You cannot have 20 mil sag there, otherwise this all gonna get crushed, the glass, and the plaster will not work. So this comes from standard, which tell us if you're designing a floor, you have to keep the deflection by this much, etc., etc. So this is what the first statement here is telling you. Serviceability, it is actually to do with making sure that damage is prevented for cladding, lining, partitions, etc. We will not go through dynamic, but again, dynamic, I can tell you some people complain about vibrations they feel within their floors, especially new home owners. When they get into a home, when they feel things are wobbly, they do report these things. But again, there is a way where the standards ask us to check things. We don't go do dynamic analysis for the timber floors. Nobody does that, but there is ways to do it. We're not going to go through this excessively in this subject. But there is a simplified way where the standard really asks us to worry about deflections due to dynamic loads. And for example, how we do it, the standards, if I want to check for residential houses, for example, they tell me, allow one heavy person standing in the middle and make sure the deflection from that heavy person will not be more than 1 millimeter. That's how we do it in a residential applications, is we allow a heavy person, about 2 kilonewton, it's more than a heavy person, and we put him in the middle, and then we want to check that the sagging that will happen will not be more than 1 millimeter. This is just a way where the standard accept it to be adequate for checking dynamic effects on floors and make sure it won't be wobbly, so you won't feel the floor is wobbly, which make things okay. We won't have these cases in this subject. I just want you to fully understand that, and this is actually done. This in all the softwares people use. These two checks are embedded in the software. So always, whenever they check deflections for beams, they're gonna have a case where that 2 kilonewton is standing in the middle of the slab and making sure the deflection is not more than 1 mil. Okay, so this was again the statement here, just telling you. After I found a deflection value, after I estimated a deflection value for a beam, then I compare it with what? All right, you compare it with the standard. And I'm not sure if it's open. I think I did not open it, guys. I haven't used it. Yeah, here we go, this one. So this is 1170. I'm trying to show you this first standard we introduced you to, 1170.0. And there's a table, this guy here. This table here it's the one we want you to practice for this week. So this table is simply gonna tell you what's the maximum deflection a beam can experience. If we're talking about floor beams, and they give you many cases here, the ratio, the span to depth ratio is this much. So if you have a beam which is spanning 5 meters, which is 5,000 millimeters, divide it over its criteria. Yeah, and this will give you the maximum deflection limit. So in this case, it's going to be 5,000 over 250, which is about what? 20 millimeters. So this is just the maximum. It's not the calculation. Remember, this is the maximum limitation. I will show you how to calculate or estimate the deflection on your beam from the loads. Here I'm talking about the limit. After you find your estimated deflection, which we will show you that later, you need to cap it and limit it with a specific value as per the standards. And here I'm just showing you a case. You just need to go through them, and they're going to tell you what loading you have on top, where the deflection is critical, is it a sagging problem or a vibration problem. And let's say, for example, you ended up with this ratio. Simply just put your span over the criteria, and then it will give you 20 millimeters, the maximum acceptable limit. Same thing if you have a swaying issue, your portal frame is swaying. They also give you suggestions if you've got a masonry wall sitting. Masonry wall, we know in industry, it's very sensitive to deflection because they got cracked if you excessively deflected them. So you see the ratio here is a bit more heavier and heavier. And instead of dividing it over 250, you have to divide your 5 meters on what? On 750, which means it's going to be much smaller. It's going to be less than 10 mil. Yeah, 10 mil, below 10 millimeters or even less. Okay, so that was the criteria I was trying to show you there. Okay, right, so now how we calculate or how we estimate. So this one here I was talking to you is the limit, delta limit. This one, where we get from the standard, is actually talking about the delta limit, the maximum limitation we have from Mr. Standards. But as discussed with you before, for special arrangements, you need to talk with the architect as well, or at least let him know, so you got it out of your site, because sometimes the standards will give you odd numbers. You just need to tell the users what's going to happen. So now I'm showing you here how to estimate the deflection. It has nothing to do with the standard. It really comes from your engineering skills you learned from mechanics of solids in mechanics of solids in semester 1, year 1, or semester 2, year 1, whenever you studied your mechanics of solids. I've just have this slide ready here from mechanics of solids. If you remember this, if you studied mechanics of solids with us, and one of the sheets we showed you, or one of the equations we showed you from, we were talking here about the bending formula, if you remember. This is just a derivation process for the bending formula. We talked about it before, and we ended up with this three-termed formulas. And one of its uses, we said that to you, is this relationship or formula which relates bending with Young's modulus, with inertia, with curvature. And we said that to you as well. We said to you we use it for deflection, right? So what I want you really to remember from here is this relationship is connected or relates to curvature. What curvature means? It is the curvature of the beam we're sagging. So this is the rho. It's the curvature of this beam. Now the center here is really very high in our real structures. If we're talking about a beam or slab, it's going to be up in the sky. Yeah, very, very, very high. But usually, so it's not useful for us to talk about curvatures. Simply what engineers do, they converted this relationship to be in function of what? Delta, the sagging. And then what they did, they come up with these basic formulas. I think you maybe done some such deviations in other subjects, but for me, I just want you to know that to estimate the deflections for beams, it simply comes from closed forms relationship. You have been introduced to you before, and you're going to be given a table like this in a test as well. Anyway, it's open book. You can open everything you like. But for example, if I want to estimate the deflection for a simply supported beam under uniform load, like this case, you use this relationship. That's it, right? If we have the beam under point load, you use this relationship. We will only test you or ask you about things you've been experiencing with us, right? We will not ask you for cases like this, when the load is a triangle, because the formula going to change. We know that, but I'm sure you know how to find it when you practice these things. So always understand the situations we cover together, and that's the process. It has nothing to do with the standard. So simply to check serviceability, you need to, the essential thing, and we spend a lot of time, we critically tested you for that, is to find the loadings, is to find Mr. W here, the loading. And make sure for the loading, you need to WSER, which most of you know how to find from the standard. The service load, make sure, don't ever put for me, please, ultimate. We don't use the ultimate. Ultimate is for strength, it's for shear check, it's for the strength check, which is making sure things will not break. For shear, bending, torsion, axial tension, compression. But when we're talking about serviceability, you have to use W serviceability, okay? Because you're going to be over designing, right? So make sure you have this point in and understand where, and I think you should know for wind as well. I said for wind, you're going to use the case of 1/25 years. That's for serviceability. So after you estimated your deflection on your simply supported beam, you're simply going to compare it with the limits, which I've already showed you where are the limits. So it's a matter of estimating the value, then comparing it with the limit. And I've already gone through that with you. So these are the two design topics we wanted to cover this week for you. It's really relaxing topics here. Now, as you've seen, and as promised, the curve is getting down now with the level of kind of difficulty. We are now just getting down. I think today's is even easier than next week. Next week, we're going to have a little bit of puzzly process with finding the compression capacity. Next week, we're going to talk about the compression capacity for steel columns. And it's going to be a little bit advanced than the rest, like tension and timber and all that. Going to be straightforward if you know what we're doing, if you are working with us in terms of spending 5 hours a week on this subject. Some general things that we have here documented, an economical approach for designers to think about when you want to design members for bending. Avoid non-compact sections. I think you know we didn't have tests. So do you know where we studied this? Yeah, kind of, or you already forgot it? Where we talked about non-compact. It's all about was with finding ZE. Yeah, and I said to you as well, this information is available in your One Steel book. So if you go to One Steel book, if you look at, I think I spent some minutes talking about this. If you go here, this table will tell you who's compact and who's not compact. Right, and I said to you as well, sometimes we're going to ask you intentionally to figure it out, and sometimes we don't want you to find it, and then you can use the ZE straight away from this book. Okay, so usually, getting back to my point here, we're trying to tell you when you design things for bending, try to use non-compact sections. They are more economic, and compact means the bulky UC sections. the universal column sections, they're heavy, as I've showed you the kilograms, they're really heavy, they're uneconomic, and you may not need them unless the architect really pushed you to do so. And that case study we're doing together, you're going to understand, because someone may ask me now when he do the authentic case study, he will tell me why you didn't use 600D beam or 400D beam. Yeah, the beam you're designing now with the authentic, up to now you had about 200 deep section. When you're going to go to serviceability, you're going to find you need even much deeper. However, I cannot go beyond what 300. Why? Because you're going to get your beam sticking out of the plaster, out of the ceiling, and it will compromise the architectural purpose there. So that's what I said to you before with the process of designing. You have to have a multi-thinking approach, not only about your design. So avoid it, but sometimes you cannot avoid. So in this case, for the authentic case study, we have to use the UC. It was bulky, heavy, expensive, but it did the job. Avoid cylinder beams. Yeah, those skinny. So actually, these two comments is kind of, it all depends on what you're doing. That's where this is, again, the thinking students, graduates, and engineers need to develop as they go into practice, because the end user, he's worried about two things: getting that job done and how much it's costed him. That's what he's worried about. Getting you that construction development done, and also how much he still have in the bank. That's what he's worried about. He's not worried about if something gonna go down. If something goes down, they will find you. So yeah, you are the one really to balance this. You can't be always uneconomic, because they won't use you for a long time. So it really comes from you. This, when you design for shear, I think I've mentioned this example many times. You cannot keep beefing. When you always, from practice, you're going to see shear is always working easily. Shear is usually works well. It's always above the capacity very well. In case you have a decent column sitting on that beam and shear failed, then don't think about just making the beam bigger and deeper. Just think about some details, like putting stiffeners, like the example I showed you. Deflection. If the beam was sagging a lot and you can't get it to work unless you go, like the case we have in the authentic case study, simply just think about cutting the span. What we mean with cutting the span, like if you have a beam, like steel beam, very long one, say 10 meters or whatever, think about putting a post in the middle here. That's cutting the span, but it all depends on the architectural. If maybe you don't have the architect or the owners want to have a free space, yeah, they want to have a gym, or they want to have something inside their house or whatever. Yeah, so it really depends on how you communicate your design with the clients and how you get it done. But typically try to reduce deflection. Like that balcony case, we can't put column in the street. We cannot put columns in the street, so it have to sag and you have to beef up your section. Right, is there anything else? Generally, yeah, I think that's typically you should use the standard sections. You don't need to complicate things. Make sure things buildable, clear on your documents. You know, beside the 8-10 criteria we have in the standards, I always think that it's the buildability criteria. I call it buildability criteria, is how the detailing you putting here, like you don't need to, if you have a column fixed to a beam, use always simple connections. Yeah, some people will say, okay, I'm gonna do it a portal frame, and he's gonna end up with overkilling details. You need to have an end plate here, he needs it fully welded, bolts here, stiffeners there. Why are you doing all this? Why are you doing all this? Because he thinks that he can have a portal frame for what? Remember, yeah, you may save your client some money in terms of the steel size. However, it's gonna cost him a lot on site to get this built. So that was this third point. Keep everything simple and use kind of standardized approach, and things gonna get. We won't ask you to design this in this subject, but just to know about buildability criteria. I personally call it buildability, so it's not only strength, serviceability, or fire. I have my own criteria to always check, is the buildability criteria to be within acceptable limits. There are some always good suggestions that we ask students to look at, like design capacity, and things gonna be like there is a lot of tools where people can use to get designs done, and you can use many things available in the industry, but you need to know how they work, because they're always going to keep some parameters for the engineers to decide on. For example, beta M. There's no software can decide on beta M. It needs someone who physically think about what's the situation and then come and decide on it. The softwares will always come up with 1.3 factor, which is always the safest. If you keep adopting 1.3, your design gonna be non-economic. So that's try to find ways, and I think that's really we done with our topic. If you have any questions, you can have 4 minutes to break or a bit more. But yeah, thank you, Vipul.
I think Haider has covered the theory for this beam design, steel beam design under the shear load. Now we'll demonstrate the examples that will help you to understand that theory, back up the theory. Now, a series of steel beams. So you have a series of steel beams, 1, 2, and 3. There are series of steel beams. So it's a part of whole system. Is 6 meters simply supported. So if you're taking this along the length, it is 6 meters. I will show it to you in the 3D. So if you just draw this beam across like this diagonally, it will have a 6 meter length. And it's simply supported. So you can think one support here, another supports down there. It is simply supported. Support on RC floor slab. So there is a reinforced concrete slab sitting on this beam. This slab is used for public hall and its dance area. So it is a dance hall. So this activity is particularly slab designed for dance training and dance activity. Connectors provided between the beams and slabs. So these beams and slab are not separated. It's shown separated in the figure, but actually it has connector like a shear connector that are attached along the length of the beam. So these are connected together, ensuring the composite actions capable of ensuring but will ensure that beam is continuously restrained. So it is fully restrained. So that condition is given. So they are asking you to design the beam A. So we need to design this beam A. We don't know what is the size of the beam. If you go to this one steel tables and there are various ranges, so we need to tell them what would be the beam A that will going to carry the bending, because you can see this beam will have this slab, weight of the slab. It will have a dancing, so load, live load. It has the ceiling that is attached. Ceiling also attached. It has 0.5 kilopascal load. So please note, generally this beam name itself is telling me that it will govern by bending. Okay, so generally the beam design is governed by bending, but as Heather mentions, we also need to make a shear check, and generally we not going back and redesign our beam. Once the beam is selected for bending, we generally provide the stiffeners to increase the shear capacity, but we're not going to change our whole beam for bending. So let me start solving these examples. Please keep this page handy here as well. So let me draw it up here. So as you can see, this beam here, let me draw this beam A, and this beam A has this slab sitting on the top of this beam. And if I just draw up the 3D part of this one, I hope you can see that. If I just draw it up this 3D, let's say this beam is going across, and there is a ceiling as well. Okay, that is attached to this one. That's what I'm designing this beam. So now I need to find it out what would be this width of this slab or the or these ceilings. How do I need to find that? Okay, let me go back to the questions. Now the question saying that you have 3.6 meters. So 3.6 meter on here. So something continuous 3.6 meter. So I can take half of 3.6. So I can take half of 3.6 and I can take half of 4.5 because the half will be carried by this beam. So only half 1.8 meter for the load, the weight of this slab 1.8 meters coming to this beam A, and 4.5 divided by 2 is coming to the beam A. So I hope you understand that. So let me go back to here. So this length from here to here would be half. So 3.6 half would be 3.6 would be 1.8, right? And then you have 4.5 divided by 2. 4.5 divided by 2, that will give me 2.25. So if I just want to plus that 1.8 plus 2.25, that will give me 4.05. So I can say that this length of that slab that is supported by this beam A is 4.05. Okay, I hope you understand that where I get this 4.05 is basically the half of this left side and half of this side will have this slab, and from this end to this end is a 6 meters. Okay, that's is 6 meters given in the question, that is spanning 6 meters. So you have a support here and you have a support here at this end. So that is the beam. So let's say step number 1, we like to calculate what is the load coming on to this beam. So let me calculate what is the load coming on to this beam A. Now beam A has a 3 loads. What are those 3 loads? Is the weight of the slab. Let me continue writing this one. So it's just weight of the slab. That is weight of the slab for this, and the slab thickness is given in the questions 150 millimeters. Okay, that is the given in questions. Now weight of the slab plus the own weight of the beam A, own weight of the beam A that has self weight, and the weight of the ceiling. So there are 3 weight that are coming on to this one. So that is the weight of ceiling. So there are dead loads and there are 3 dead loads, and there are live loads as well. So that live load we're going to calculate using that equations that we have or the tables that we will have. So the dead load, now weight of the slab. Now the density of the slab will be given to us. So let me go and work it out. Let me work it out that density of the slab given, which is 25 kilonewton per meter cube, given in the questions. Let me go back and write it. So 25 kilonewton per meter cube, and then you have this area, that we already calculated, 150 meters. That is the thickness of the slab, and this perpendicular length, so 4.05 meters, right? So that's the area. So now if I work it out this one using the calculators, I would have some answers. Let me work it out. What would be that answer? So 25 times 0.15 times 4.05 would gives me 15 kilonewton per meter. That is the dead load coming due to the weight of the slab. I hope you understand this weight of the slab. Any questions there? So first we calculate dead load 1. Let's say dead load 1 is the due to the self weight of the that beam due to this slab. So that is the weight of the slab coming on to that beam. All right, now next one, let me calculate the next one is the dead load 2 due to these ceilings. Now these ceilings has 0.5 kilonewton per meter square, which was the kilopascals, right? It's given in the questions. Let me show you that 0.5 kilopascals, that is the weight of the slab, weight of the ceiling. So if I have that 0.5 and the length, perpendicular length is 4.05 meters, I would have, let's say 0.5 times 4.05, I would have 2 kilonewton per meter. So I have now 2 weight value that I have calculated. One is 15 kilonewton per meter, and another one is a 2 kilonewton per meter for the ceiling. Now the third one, that weight of the beam A. Now let's say this beam, when you have simply supported, length over D ratio is 20 millimeters. So this length times the depth of the beam is 20. Now, where is this coming from? I think this one coming from, in the test we will give you this one. That is just the assumption that if you have simply supported beam, due to the deflection, we have limitation that length to the depth ratio is 20. Generally, these are coming from experience. So if you have designed many beams, you will find that, okay, deflection of the beam control that will go on by the length of the beam. So that is length of the beam over the depth of ratio, it should be limited to 20. So if I want to calculate D, I can have a length over 20, and the length is given 6000 millimeters, because if you consider this length of the beam, this beam number A, then you have 6000 over 20. I would get the answer around 300 millimeters. Okay, so I will say that I need some beam which has a depth of 300 millimeters, right? So where should I go and check it? I can go to this one steel tables. I think you have access to one steel table, and we are looking for a universal beam. So if you go back to the universal beam section, taper beam, universal beam, let me check out. There you go, universal beam. There you go, this is the universal beam, and there are various ranges given to you, starting from 600 depth to the 150. Now we are looking for something close to the 300, as you can see. So let me check this 310 UB40.4. I would select this middle one. Let's say 310 UB40.4, and that is arbitrary. Okay, some might will select this value, some might take this one. It's iterative process. We don't know whether it's gonna work or not, but let's say that I select this 310 UB40.4, which has a depth of 304. So let's select 310 UB40.4. Okay, so that's I just selected for this particular beam based on this L over D ratio. Now 40.4. So the weight of this beam is telling me that 40.4 kg per meter. Right? Where is coming from? Because all these numbers here, that's telling me that is the weight of the beam, self weight of the beam. 40.4 is the weight of the beam, and the unit given kg per meter here. So this is the weight. So what is telling me? If you take a 1 meter beam, which is 310, that will weigh 40.4 kilograms. So if you have a beam, I can show it to you, this beam now. So if you have this kind of beam, this is not a universal beam. I think that is taper flange. But if you have this beam and if you just cut it 1 meter and if you put it on the scale, it will weigh 40.4 kilograms. That's what it's saying that. Okay, you don't need to do it. The catalog's telling me that they already done the weight for us. So okay, I have 40.4. That sounds good, but I need this in the kilonewton per meter because I have the weight of the slab in kilonewton per meter. I have weight of the ceiling 2 kilonewton per meters. Then what would be this one? Okay, that's fine. I can just convert this one first into the newton by multiplying them. So that will give me 404 newton per meter, and then I divide by 1000, so I can get 0.4 kilonewton per meter. Right? So that is the weight of the beam. So if I just want to know the total weight of the total dead load, so the dead load, let me, that is denoted by G, is weight of the slab. Weight of the slab is 15 kilonewton per meters. That beam will carry 15 kilonewton meter slab, plus the weight of the ceiling is 2 kilonewton per meters. That's fine. Okay, and the own weight of the beam is 0.4 kilonewton per meter. So if I add them all, 15 plus 2 plus 0.4 will give me 17.4 kilonewton per meter, and that is the dead load. That's load coming on to this beam A. Okay, now the live load, let's say live load, and live load represented by Q. Live load is represented by Q. Now where are we going to look at the live load? I think we need to use these standards that I'm going to show you here, okay, in a minute. Now the standard that we're going to use to get this live load is 1170.1. Yep, I think you know the standards. 1170.1. If you go to the table 3.1, I think you know the standards. You done this one many times. There, table 3.1. It has give you all these different live load. A is a domestic and residential active, office. Now C is area where people may congregate. So I think C looks promising because it's a dance floor. Let me go through the C. If you go through the C1, C2, read through this. In the C4 sections, I could find some promising name. It's called Dance Halls and Stadium Gymnasium, an area with the possible physical activity, and I would take uniformly distributed action 5 kilopascal. So if I have a dance hall, I would take these 5 kilopascals. I think that looks promising. So this slab where the people will have a dance on it, the standard saying that you can have a 5 kilonewton per meter square. So it's saying that every meter, if you take just meter by meter, it says that you have 5 people. If it is 100 kilogram each person, it says that you can have 5 people sitting into the 1 meter by 1 meter area. If I take 1 meter, you have 5 people dancing into that one. Okay, if you invite additional. So they said, okay, maximum 5 people allow in 1 meter. That's what I've designed. Okay, that looks okay. 5 kilopascals, where is coming from? It said AS1170.1. It says you can put table 3.1 and say that in the page number, let me write page number 10. Okay, let me put next to here. So it's on the page number 10, table 3.1. Let me put this section as well, section C4 and C4. It says that 5 kilopascals. Okay, but I need in kilonewton per meters. Okay, I know how to convert this 5 kilopascal, which is basically kilonewton per meter square, and then I multiply this width. Okay, perpendicular distance. We take those examples that, okay, if you have the UDL load coming, I can multiply this 4.05. So let me multiply 4.05 meters. So I can say that 5 times 4.05 meters is give me 20 kilonewton per meter approximately. All right, sounds good. 20 kilonewton meter live load and dead load is 17 kilonewton per meter, 17.4 kilonewton per meter. All right, perfect. I think so far so good. There is no any issue. Now the standards will going to tell me some of the details that I think we need to multiply these load factors. Okay, let me tell you where it's supposed to be given. So if you go to the one more standards. Down part 0, let me find it out, part 0. Okay, I found part 0. Now if you go to the part 0, 1170 part 0, 1170.0, you will go somewhere close. Yep, there you go, close 4.2.2. It's telling me that if you have a strength, which is the bending strength, shear strength, that is the strength requirement. Okay, we are checking for strength, that is the safety of the structures. Now, if you have safety of the structures, they said if you have a dead load and live load, you must multiply your dead load by factor 1.2 and factor. So that is called load factors. Now, let me tell you something. When you design these structures, they say that your dead load would be increased by 20% and your live load will be increased by 50%. So what does it mean? Okay, guys, you calculate this one. If someone invited more people here and sometimes the people start standing next to each other and sometimes they are more live load, so you need to multiply that. If sometimes they have some let's say some special event and they bring a lot of furniture into this one to attend those ones, so the live load and dead load will be vary, because 20 live load sometimes you might go up, right? It's not always 5 people standing in the 1 meter square. So say that, okay, standard said that's okay. You can calculate your total design load, saying that you can multiply 1.2 G with the dead load, and you are basically increasing your 20% dead load. And so G, total G was how much? 17.4. That's fine, 17.4. Live load, we got 20. That's fine. I think we can get that 1.2 times 17.4 plus 1.5 times 20, which gives me around 51 kilonewton per meter. Okay, so that's load that I got 51 kilonewton per meter is a total load. So basically we are not adding this one. So look at that, 17 plus 40 is 34, around 35 kilonewton. But standard said, well, 35 kilonewton meter. No, just design it 51 because we need a safety. We don't want people to dance and they just fall. We're making sure that these people are safe. We don't want to kill them. Okay, the structural engineer's job to keep them safe, keep dancing them. Okay, for a long time. All right. Let's finish this story. We done this one. Okay, now let's do the structure analysis. First, we done the load calculations. Let's do the structure analysis. Structure analysis meaning the mechanics of solid. Let's do this structural analysis. What is structure analysis? Let me redraw this one. That this beam, that this starting from this point, so this point here, that is this point here, and let's say this is supported, simply supported. Let's put the roller here. Okay, then let's say supported by column or something here, and this has a UDL load. Yes, that has a UDL load because of the live load and dead load we calculated. That is fine. I put that live load. What is the length from this point to this point? I can say that from this point to this point is 6 meters. I can see that given in the question. So I can put 6 meter here. What was the load again? He said, okay, 51 kilonewton per meter. Okay, 51 kilonewton per meter. That is fine. Now, shear force diagram. I think by this time, I think you should know by heart. I think they should be equal. Okay, just cancel that. It should be equal and in the middle. All right, so this is WL by 2. That would be your shear force, and WL by 2. What was the W? Was 51. What was the length? 6 divided by 2. So if I just do this one here, 51 times 6 divided by 2 give me 153 kilonewtons, right? So I can say that this shear force is 153 kilonewtons. This shear force here 153 kilonewtons. That is fine. What would be the bending moment diagram? So you can say, okay, this will be WL square over 8. Okay, that is the maximum moment here. So that's fine. WL square over 8. I know the load was 51. I know the length is 6 square over 8. Let me calculate that. 51 times 36 over 8. It gives me 230 kilonewton meters. So that would be 230 kilonewton meters. Okay. Now we need to select the beam which can resistance this 230 kilonewton meters. Okay, that's what the intention is, and then we will go and check for shear as well. Let me continue solving this one. Is there any questions so far? I can stop here. It's just revising the, I think we are revising this bending from the last 2 weeks. Okay, so it's again repeating what we have done so far. All right, let's start solving this one. Is there any questions, or I can stop if you don't understand anything or anything? So far so good. Structure analysis done. Now let's do the third one. Let me see that we will have a design for bending. Okay, we always do design for bending first. We never do the shear check first. We always do the bending first. When the beam is strong enough to carry these 230 kilonewton per meters, we are safe. This is called design bending moment. We call it, sometimes we denote it by M star. M star is the design bending moment, and this is V star. V star is the design shear force. That design bending moment is coming from your bending moment diagram. That is the maximum moment in the bending moment diagram. And the design shear force is basically obtained from your shear force diagram, which is maximum shear force in your shear force diagram. So in our example, M star equal to 230 kilonewton meter, and the V star is 153 kilonewton per meter. Very important. We need to use these values over and over again. Now, first we never start with shear because beam will not going to fail in the shear. Okay, we do the check, but we always do the bending one first. So bending moment diagram, bending design 230. So let's make some assumptions. Let's use 300 grade steel. Okay, that is basically the 300 megapascal steel. Beam is fully restrained. If you remember from the last week, what is meaning by fully restrained, that we generally calculate the section moment capacity, right? So fully restrained means this beam will not have this kind of lateral buckling. It will not gonna come out. It will not gonna kick off. It will have this restraint. They have these stiffeners. They are attaching to the beam and with the slab. So these are fully restrained. So it will just govern by this section capacity. Now for fully restrained, we know that 5 msx is greater than mx star. Where is coming from? I like to show it to you. I think if you go back to the bending sections, this is a shear one. If you go all the way to the bending, I can revise you that one again. There you go. At the start of this section 5, it will telling me that the capacity of your beam, whatever the beam you use, whatever the beam that you're going to use it here, whatever the beam that you're going to use it, that capacity 5 ms should be greater than your m star, should be greater than this one. You should select the beam which has a capacity greater than mx star. So that's what it's saying. Okay, I just write this one opposite, so that's become the greater than, but they are equal. Okay, they are same. So that's the here, and beam will bend about the x-axis, the strong axis. I think if you go back to this one, this beam will bend about this x-axis, so it's about the strong axis. So therefore we take it x. Okay. Now the beam will going to bend about this x-axis, and then 5 capacity factor 0.9. Where is coming from? I will explain you that capacity factor. Let me take you through that one as well. I think there is a table at the start that it will have a capacity factors. Capacity reduction factor, table 3.4. So if you go to this table 3.4, capacity reduction factor 0.9, table 3.4. Where is it? For members subjected to bending, for all these fully restrained, we will have this 0.9 capacity factor. So that is capacity factor. Now I need to calculate this MSX. So if you just go back to the bending section, I think section 5 was there. And then you have this equation for section capacity MS. So section capacity MS is equal to Fy times Ze, which is section modulus, greater than or equal to MXX. Right? So far so good, no problem. Capacity factor 0.9 given in the table 3.4. This is given in the clause 5.2.1, greater than or equal to MXX. All right, now we know this MSX. What was that? That was 230 kilonewton per meter. We know that. Okay, let me put that 230 kilonewton per meter. Now I generally need this one in the Newton, so I just multiply by 1000 to get it into the Newton, and I multiply again to convert into let's say the unit is Newton millimeter. That is working. So I multiply by this thousands about 2 times. I know this 0.9. I am using 300 grades. Most of them are 300 megapascals. So that is Ze. So if I just move it across, Ze equal to 230 times 1000 times 1000 over 0.9 times 300. Right? I hope you understand that. It's a very simple one, and I can use the calculator. Let me put 230 times 1000 times 1000 divided by 0.9 times 300, which will give me around 851 times 10 raised to. So saying that you need 851 times 10 raised to 3 millimeter to the cube. Okay, so he's saying that you should select the beam which is 851 times 10 raised to minus 3 millimeter cube. Now someone might say, what happened to your beam that you selected 310 UB 40.4? Why you are not using that beam? Okay, this beam that we use it for calculating the self weight of the beam. We don't know what is the weight of the beam. Now to estimate the approximate weight, we selected the beam based on this deflection check. Okay, this L/D over ratio, they are generally designed for the deflection only. So this is a good approximate. That is the good approximate starting point, that we need to take into account some weight of the beam. So we don't know what is that weight, but I think this is just a starting point. But we don't know whether this beam will have the enough capacity to carry the bending or not. So therefore we done this check. So we can have 851 10 to the power 3. Now we have this section modulus 850 10 to the power 3. So I need to go back and do it here. Okay, we was selected this 40.5, right? If you remember that we will have this 40.5. Let's say their ZE value for that would be that will not have enough. You can see they are 569 633. Okay, so they don't have enough. So I need to go up. I can go up, and I can find something promising value of, let's say 897. I think I found it. So I can take 360 UB 50.7. I can lift it up for you. So I can have this 50.7 360 UB, and I can take this value, which is how much was that? 897. Okay, so I can have this 897 because I need to select something from 851. So I can select 897. Please note this 40.4 is not enough. Okay, so therefore we just go 897. So let's select this 360 UB, and it has a ZE value of 897 times 10 raised to minus 3 millimeter to the cube. So that is okay, because you need 851, something more than 851. Now so we selected 895 and 360 UB 50.7. Now someone might come back and say that, oh, Vipul, your 40 kilogram of beam in every meters, and now you are saying that 51 kilogram every meters. What happened to this 10 kilogram? Yeah, of course, you can go back and just put these 300 UB 50.7 and you just recalculate. It's just 0.5. Please note, this is 0.4, 0.5. Rounding up, this 17.5 will be, we will not gonna make huge difference here. We will not go, we will live with this one. But in the real world, if you want to do it, you can just go through it, and again you put this kilogram and so on, but it will not be huge. This 0.4, this 50 kilogram become 0.5 here, 17.5. I already rounded up this one to this some value here, so it will not going to make a huge difference. Okay, but you are more than welcome to do that. But this 897 has this 360 UB. They will satisfy the bending criteria, right? So everyone happy? So this beam 360 UB, let me put here, this 360 UB 50.7 is okay for bending, right? So it will have enough capacity, because if you just multiply 300 by this one, let me do that. So let's say 897 times 1000, that is Z, times by 300 yield strength, times by 0.9. What is the capacity? And let's say divide by 1000, divide by 1000. So it will have a 242, and we need 230. Yeah, that is okay, right? So this beam which we selected 360 UB 50.7, it has a capacity of 242. It has this 5 MSX has a capacity of 242 kilonewton meters, right? And that is greater than your 230 kilonewton. So bending is okay. There is no any problem for bending. Okay, and that is always the check. Okay, this is beam, and beam are generally governed by bending. So we should not fail the beam under the bending. Now here 50-50. Okay, we can do it. Okay, we need to check it, but this design will not govern for the shear. Okay, let's do this here. So we done this third step, design for bending, and the bending check is okay. There was no any issue. And let me do the design for shear. Okay. Let me revise you all what we done so far. So here we done the calculation for load. Okay, the calculation of load involving this weight of the beam, weight of the slab, weight of the ceiling, dead load, live load. People are jumping here with for the dancing, and the standard saying that okay, if you have a jumping people here, dancing people here, you need to have 5 kilopascal, meaning that 5 people every square meter. Okay, that's fine. The still standard saying that okay, still I'm not satisfied, it's not safe. Said increase your dead load by 20%, increase your live load by 50%. Okay, that's done. 51 kilonewton per meter. Then we done the structure analysis, because structure analysis is very important. We done the SD1. If you remember that SD1, students are jumping up and down with the marks and all, saying that oh, SD1 bending moment diagram, shear for that, very important. The design will not going to stand without the structure analysis. Structure analysis is always done before the design, so very important. Mechanics of solid and SD1. So we done the shear force diagram and bending moment diagram. Okay, so we have shear force. We start 153, so we make sure that beam will have enough shear resistance, and we have bending moment diagram 230 kilonewton meters. So saying that okay, I need to find a beam which will have a capacity more than 230. So the standard said okay, these equations, we substitute these equations and we find a ZE value which is 851, and then we go to this one still table and saying that let me find something which is more than 851, and then said 897. So that is perfect. That's no problem. All right. So that's what we done so far. Let me start writing for shear. Now shear, we will have two possibility. What is that possibility? We will have a failure to check. Check the failure. What is the failure check? You have two options. One is yielding. It will yield before it buckles. Okay, so meaning that is a compact section. Meaning compact section meaning your beam will have a strong wave. Meaning that this, let's say this one is this is the wave, it is strong. Let's say you have another beam which is very tiny wave. Look at that. Okay, so this will yield, that will yielding. Okay, it will have less trouble. So we have wider thick one, and the next one is the buckling. Okay, this will buckle before it yields. So this will have buckling. Now, well, this is the pictures, but the standard saying that all right, I will make your life easy. What the standard is saying that okay, I don't know whether what you're talking about, this thick or small. But I can give you the magical equations. Always standards give a magical equations. If you come back to this design for shear clause 5.11, you are more than welcome to read all of this. But it says that okay, if your dP over TW value is less than or equal to 82 Fy and 250, please make a check. And if this happens, saying that you have yielding. Very simple. Okay, you don't need to look at the picture whether it's thick or small, but it will telling me that okay, if these things happen, then you have yielding. Okay, that sounds promising. Then they said okay, what about if you do the check again, and if this happen, and saying that you will have buckling failure. All right, so we need to do this check, guys. Okay, dP on TW. What is dP? Is this the width of the wave, which is between this value, and TW is the thickness of this wave. All right, where can I find it? Please remember what the universal beam we are working, 360 UB 50.7, 360 UB 50.7. So let me put that 360 UB 50.7. So for this one, can you tell me dP on TW? Of course, I can tell you. We can go to this one here, 360 UB 50.7. That was D1 TW. Come all the way 45.6 or something. Yeah, 45.6. So there was 45.6. That is D1 over TW. Okay, so that D1 is given here. So it says that dP on TW is 45.6. Perfect. All right, can you please find that one as well? So it says 82 on square root Fy on 250, 82 on square root 300. Why you take 300? Because we assume that is 300 grade, and it will not going to make much difference. You know this 360 UB50, you can take this 320. It will not going to make your huge difference. So you can take 320, but still it is acceptable. So I just use the 300, which is still conservative. Okay. And we assume that is grade 300. I can show you to you where we assume it. Yeah, 300 grade, we assume it at the back. So if I just use this calculator again, square root 300 over 250, that will give me 1.09. 82 divided by answers, give me 75. So that is fine, 75. Let's check. That is 46. 46 is less than 75. Yep. So left hand side, which is 46, and right hand side, which is 75. So 46 is less than 75, meaning left hand side is less than right hand side. We will have yielding. Okay, so we not worry about the buckling. We falls in this yielding. Okay, so that's fine. We are in this zone when the maximum web panel depth to thickness ratio satisfy this. Your capacity VU, is equal to VW. Now what is VW? VW is a shear yield capacity. VW is shear yield capacity. All right, that's fine. How can I find this VW? Very simple. For wave, you can have 0.6 Fy times AW. Right, 0.6 Fy 300. You assume grade 300. AW. What is AW? AW is basically the area of your wave. So let me put that area of the wave here. You are talking about this. What is this length? Well, I can get it from the one steel table. 360 UB 50.7, and the D1 is, there you go, 300. So that is 300 here, 300. And the thickness of the web is 7.3. that is given here. So I can put 7.3 here. So the area would be just 333 times 7.3. All right, simple. 0.6 times 333 times 300 times 7.3, which gives me 437,562. And that will have a, let me see, we are going on the right track, right? And then we will find this VU nominal. Okay. Let me check my solutions. Okay, so far so good. 437. Now that VU equal to VW equal to 437, you can just divide by 1000, two times. So, or just a kilonewton, so just one time. Divide by 1000, give me 438 kilonewtons. That's the capacity. What is this 438? 438 is basically the capacity, shear capacity of this beam based on the material and based on the geometry. It has capacity. Okay, if you increase this thickness, its capacity increase. If you increase the strength, it's like how strong the beam is under shear. Okay, so the how strong 438. Now the standard saying that, okay, what people, you make some mistakes and all. Engineer always make a mistake. So it says that you reduce your capacity by 10% by multiplying your reduction factor. So that's okay. I say that, okay, 0.9 times 438. So I will have 394 kilonewtons. Right. Okay. So let me check 394. Let me check 394. What was the shear force? Well, we need 153. And how much we got? We got 394. Of course, we need, how much was we needed? 153. We needed 153, but our beam is 394. Look at that, very big. So 5 VU is far greater than 153 V star. Okay, because that is 394 kilonewton, far greater than 153, that is okay, right? So this beam is okay. Look at that, shear capacity is very high, then you are required 153, 394. So we need more than 153. If you get 160, 170, I'm very happy. But your beam will not going to have strong enough for the bending. So therefore, shear generally will not give you trouble. Okay, generally they satisfy these conditions. I think the conditions given here, that V star value should be greater than your 5 VV, and VV is just your nominal shear capacity. That VV is equal to VU, VU is equal to VW. So that's what we done. Any questions? We have 15 minutes. Someone asked. All right, now serviceability. I think I will give you 5 minutes or 10 minutes for this lab reports things. Okay. Now last one, serviceability. What happens here? The beam is strong enough to carry the beam and the bending. Now for serviceability, the beam generally is strong enough. So for serviceability, we can have a short-term loading. Now someone will say that what happened to this load? Why can't you use these 51 kilonewton per meters? Why are you recalculating your service load? This is called service load. This is called service load. This is called service load. This is called your design load. Okay, so this service load is basically your beam is strong enough. Your beam is not will fail. No one will going to die. No one going to kill. That is the main purpose. Now, whether the beam will going to have a lot of deflection, vibration when people jumping up and down, it should not be vibrate, right? So say that okay, you can have your dead load. What is your dead load? Was 17.4 kilonewton per meter. What would be your this value? So you can go back again to the standards, and I can show you to use the serviceability steps. So over here you will have table 4.1 in AS4170.0. You will have these short-term load factors, SIS. So residential, domestic, office, parking, retail, storage. I think we are done. So floor for dance, and there is no given, so it's just 1. Okay, so we take it 1. What was the live load? Live load was 20 kilonewton per meter. So it's just it would be your just I think 37.5 I think. So that is 37.4 kilonewton per meters. All right, now we are very close now. Let me show for simply supported beam. If you are talking about the simply supported beam, and you can go to SD1 lecture notes and we calculate these deflections. If you remember that deflection was calculated by WL to the power 4 over 384 EI. Student was asking me SD1, why are you not giving me the value? Why you put this always variable? I'm not comfortable using those variables. Well, the reason is here. If you keep putting the variable, you don't know these equations. So in these equations, this loading, please note, this loading is your service load. This loading is not your design load. This is a service load. I repeat, for your deflections, you need the service load. This is not for the strength. This is for the serviceability. So we use this 37.4. Length of the beam was 6,000 millimeters. So if you remember that, 384. The Young modulus of the steel, 200,000. Now, where would be the Young modulus of the steel? So the Young modulus of the steel, I think if you go back to the start of this and do that, oh, they have given you here. So the Young modulus alphabetical order, E value, here you go. Young modulus of the elasticity, 200,000 for this one. So that's coming here. Now what beam we are using? 360 UB. What was that? What was the beam that we using it? Let me check. We selected, oh, there you go, 360 UB 50.7. So we can find out IX value. For here, 360 UB 50.7, and then you have a Ix value here 142 times 10 to the power 6. Don't forget to multiply this one with the 10 to the power 6. So I can have 142 times 10 to the power 6. So if you use the calculators, you will get, let me see the answer. You will get this 22.4 millimeters. Now, whether we're going to whether it is good or not, so the standards will give me the deflection limit. Now the deflection limit is span over 250. Where can I get it? If you go to the table C1 in AS4170.0, if you go to the table C1 on page number 27, there you go, we are very close. There you go, they have given the serviceability limit state criteria. And if you come back here, very close to the floors and floor, and then you will have this beam with the line of sight is across, sagging, mid-span deflection, your loading plus this live load with a span, so span over 250. So that's the limit. How much the span was? 6,000 over 250. So standard saying that you can't go 24 millimeters. So you said standard saying that if your people are jumping up and down, you can't have deflection more than 24 millimeters. All right, so 22.4 was less than 24 millimeters, so I am okay for this one. If this not happens, you need to go back and do it again, the checks. Okay, all this you need to increase this. You need to increase this beam here to satisfy the service. But I think here is okay. 22.4 millimeter. It will have a deflection of 22.4 millimeters under this loading, but standard state 24 millimeters, you are okay. If you go more than that, then your beam is not okay. It's not serviceable. I think that's the end.